This demo focuses on the use case 1 scenario to showcase the advantages of using the VO stack in complex robotic software implementations in emergency and disaster scenarios. More specifically, it shows a navigation, mapping, detection, and assessment solution in an unknown environment. The application graph includes multiple components being deployed as containers in a Kubernetes cluster. The virtual object, or VO container, is at the core of the demonstration. It acts as a virtual abstraction of a complex physical robot, enabling flexibility and interoperability with other application components. Each node in the graph represents either a VO, a composite virtual object, CVO, or an application-level component. The communication from the VO to the physical robot is via Xeno protocol. CVO integrates multiple VOs and provides higher-level functionalities. The interface enables an HTTP communication towards the GUI container.
The WSN gateway centralizes data pushed by the sensor nodes to an MQTT broker. This gateway also runs a VO stack service to send events to its VO3. This VO stores data into an influx database. The VO is also consumed through HTTP by the WSN Planner and Controller API.
To start with, we deploy all required containers and services on the Kubernetes cluster on our cloud infrastructure. This includes the web application to interact with the VO and a Foxglove dashboard to display the robotic messages and data. Using the web application, we can interact with the robot device through the VO abstraction. In the GUI, we can start-stop mapping, save map, start-stop cameras, deploy sensors, detect liquid, assess person status, and sample the liquid. We can also read the properties on the robot and save 2D map and ROSBAGs on the VO database. After launching the start script, we can see in our Foxglove dashboard container the RAWS topics being displayed. Here we see the camera stream, the LiDAR information, and the virtual representation of the robot, GPS coordinates, annotated images in the dashboard. Here are our robots. On the left, we have our customized drone, built on Holybro X500. It features a Jetson Orin Nano companion computer and a Z2i depth camera for onboard processing and 3D perception. On the right is the Summit XL, a ground robot equipped with Mecanum wheels for omnidirectional movement. It integrates a UR5 robotic arm with a gripper, 2 cameras, GPS module, and 2D LiDARs, enabling it to perceive and interact with complex environments.
A wireless sensor network is deployed during one of our sub-scenarios by the Summit XL robot. The network is structured around a WSN gateway, based on a Raspberry Pi 3 Plus. This Raspberry is connected to the Indiana 5G gateway, and it runs a VO stack service to communicate with the sensor nodes. These sensor nodes are powered by PICOM devices, which integrate various environmental sensors such as temperature, humidity, atmospheric pressure, and more. The microcontroller offers Wi-Fi and Bluetooth connectivity, and runs MicroPython scripts to communicate data to the Raspberry Pi gateway using the VO stack formalism.
During the demo day at the Luca Koper port, our robots were deployed to simulate an emergency scenario involving a fallen container, showcasing how autonomous systems can assist in such critical situations. A phone call was placed to alert the firefighting and security teams to respond to the fallen container emergency at the port. The security team quickly arrived to secure the area, clearing the way for our robotic team to step in and begin the mission. Multiple drones were active during the demonstration. The chief operator managed the overall airspace. Our drone did the operation, and the Einen drone filmed the mission. The first mission involves drone-based mapping. On the Foxglove dashboard, the top left displays a 2D map of the area, while the bottom left shows the 3D reconstruction along with the drone's flight path. The top right features live video streaming from the drone, and the bottom right presents the drone's GPS position overlaid on the map. The second mission focuses on mapping and detection using the Summit XL. We initiate the task by triggering ROS processes on the device, which launches the 2D mapping, front camera, and the arm camera detection. Once running, the Foxglove dashboard visualizes the active ROS topics. These include the real-time 2D map, live camera streams, LiDAR data, a virtual representation of the robot in motion, and annotated images highlighting the detected objects in the environment. One of the primary objectives in this mission is person and liquid detection, critical for assessing emergency situations. We use tiny YOLO V4 for real-time person detection and a liquid detection model to identify potential spills. Detected elements are marked directly on the map. Red indicates liquid, yellow marks a laying person, and green represents a standing person. Another key task is mapping, providing crucial spatial awareness for both operators and autonomous systems. 2D maps are generated in real time using LiDAR data, offering a floor plan-like view for navigation and planning. Simultaneously, the arm camera builds a 3D reconstruction of the environment, enhancing object localization and visualizing complex structures.
The third task in this use case involves sensor deployment, which is where the WSN Planner and Controller application comes into play.
To manage the wireless sensor network, we developed an intuitive web application called WSN Planner and Controller. This app allows us to create pre-configured missions with default settings. For the demonstration at Luca Koper port, the default setting starts with 2 Pi senses and 1 Raspberry gateway. We can choose which sensors to activate on each node. For this demo, we didn't need the accelerometer. A summary screen lets us name the mission before launching it. Once configured, we place the selected nodes on the robot and wait for it to be ready. The WSN app then waits for the map sent from the robot to the VO, the CVO, and the WSN API. Once received, the map is displayed in the web app. The right side shows live map data from the robot. The left side shows the list of nodes selected and installed on the robot.
First responders can now select where to place the sensor nodes on the map. In this demo, both nodes are placed around containers in the risky area. These coordinates are saved and sent to the CVO using the VO stack. The robot moves to the specified area to position the nodes. The first sensor data is sent to the Raspberry Pi gateway, then to VO3. The WSN API can retrieve this data that can be displayed in the web app.
We can click the button at the top right to view an ongoing mission. On the graph, we noticed that the PiSense node ending in 9C is not working anymore. We can select a backup node ending in A4, configure it and mount it on the Summit XL. Here we choose to only activate the temperature sensor. Up to 2 nodes can be deployed at a time. Once the coordinates are sent to the robot, it moves again to the designated location and the same process is repeated to receive the sensor data.
To conclude, thanks to the use of modern web frameworks, we implemented an efficient WSN planner and controller. Let's take a closer look at what happens when the robot receives the coordinates from the WSN web app.
The robot autonomously navigates to each location and uses its robotic arm to deploy the sensors. In this demonstration, the robot successfully navigates to and deploys 2 sensors at their designated positions, highlighting its ability to perform delicate tasks in a structured, real-world setting. The final task is liquid sampling. The coordinates for sampling are obtained from the liquid detection and localization process. Sampling is initiated through the Flask GUI, which sends a command to the robot to start the mission. The robot autonomously navigates to the target location and uses a cotton swab attached to its gripper to collect the liquid sample, placing it back into the pallet afterward.
To conclude our video, we would like to highlight some initial results that we are proud to share.
To assess the full scope of the use case, we evaluate 2 types of KPIs, quantitative KPIs and 1 qualitative KPI, a survey submitted to first responders involved in the demonstration at Luca Koper port.
Victim detection and assessment. This KPI measures how accurately the system detects and classifies victims. In tests, both precision and recall were perfect. No false positives or false negatives. Time to task completion. Our system outperformed all targets. Mapping, sensor deployment, liquid sampling, and victim detection were completed up to 20 times faster than expected, enabling swift and effective emergency response.
Thank you for taking the time to watch this video and for your valuable support.
For more information, please follow these links.